All right, so now I'm going to tell you a little bit about, so yesterday I talked about how to use OpenPath sampling. Today we're going to talk about developing for OpenPath sampling because that's what you all are going to be doing over the next week and a half. So again, the talk materials are available in the same place as before. If you got that yesterday, you will need to do a git pull to bring down the newest stuff from this because I just put it up there today, a few minutes ago. So this picture, again, this thing is going to be what you live your life by as far as I'm concerned for the next few days. We'll talk about these things again in this order. We're going to talk about developing dynamics engines, which is what some of you are going to be doing. We're going to talk about how we work with collective variables, again, what some of you are going to be doing. I'll talk about something that sort of overlaps between the differences between collective variables, volumes, and ensembles, more as a conceptual thing because it's something that I think people often get confused on. And then we'll talk a little bit about this whole networks, transitions, ensembles section because that's, again, something that might have some relevance to some of what you're doing. A few of you are going to be working on new path movers, so I'll talk about path movers and move strategies. Fortunately, you don't have to worry anything about sample set. Actually, we talked about the details of how a sample set is structured yesterday when I was talking about the analysis. And you also don't need to worry about, well, we're going to talk about storage. You don't need to worry about subclassing storage, but you need to understand how everything that you make can get stored into our files. And I'll say a brief thing about path simulators too, because if you're looking at doing something like adding PPTIS, I think PPTIS can be done with our existing path simulators, but if you were to do something like FFS, that would require a new path simulator. Before I get into that, though, I'm going to start out by talking a little bit about source code style. This is building off of what Alan talked about already. So you'll notice at the beginning, Alan was talking about how important it is to have good variable names, how important it is to use a style that's understandable. And you'll notice that some of us who have done a lot of programming along these lines and have talked about these best practices, I know me and I saw John nodding our heads saying, yes, this is really important. So there are a few things that we do with OPS. The first thing is the source style that we use is PEP8, which is the Python standard, and I'll show you that in a moment. Then we document our code using Sphinx, which is basically the same tool that's used for the eCam documentation, uses RST inside comments within OpenPathSampling code. We use what's called the NumPy doc format. Now, if you noticed in Johnny's talk, there were all of the, he had examples of code from OpenPathSampling that had all these examples where at the top of everything there was a bunch of comments with a big description. Those are the documents, those are the things that you should always write when you are writing code. So let's just take a quick look at this stuff online. Well, first off, there's the OpenPathSampling documentation itself at openpathsampling.org. And if you go to Overviews for Developers, you can find links to these same information under coding style. PEP8, we allow for readability. Actually, that's within the PEP8 guidelines, but readability is what matters most. Probably should be capitalization of variable names, not nams. And NumPy doc. So the links there, this is the link to PEP8. We don't need to be highlighting things. I'm not going to go through all of it. You should skim over it if you aren't already familiar with Python style rules. The first important thing, a foolish consistency, is a hobgoblin of little minds. If it's not readable, that's the only thing that matters, is readability. So don't follow the rules without, or be willing to break the rules in the name of readability on occasion, but rarely. The big things, 4 spaces, no tabs, always spaces. There are rules about how you break a function over multiple lines. There are rules about how you do indentation and how you do spacing. Let's see. Max line length, 79 characters. This is one that we really prefer you try to stick to. There are rare occasions where you can break that. But some of us, like me, work on an 80-column terminal. And so we do prefer to stick to the 80 columns or less lines.
Does that mess up your stack of punch cards otherwise?
Yes, it does. It messes up my stack of punch cards. Whippersnappers. So this is one that's actually kind of weird, that when you should put a line break relative to a binary operator, you're actually supposed to put it like this, which makes sense. In addition, it's a little bit weirder sometimes when you're doing logical binary operators, but this is the rule in PEP 8. There's a lot of stuff here that you should look at. Most of it's not too terribly important. I mean, yeah, you can figure it out on your own on the way. There's a lot of stuff that's like this. Let's see. How you do spacing, where you need to be careful. In particular, let's see. This is a no-no where you have a big bunch of white space, so you've evened up the equal signs. This is not allowed in PEP 8. Let's see if I can find. Here is an important one also that you'll often see mistakes on, that if you are using keyword arguments, there should be no space. Unlike this, that's an important part of how that should work. It improves readability a lot because we expect it to look that way, and it's confusing if it doesn't. So anyway, the link is here. You can read more about it. If you have any questions along the way, you can also look in our code and follow the examples as we lead. NumPy doc style, this is what's used in NumPy and SciPy. There's the other main style that's along for Python code is on this kind of documentation is the Google style. So we do not use Google style, we use NumPy doc style. And there are certain rules about what you do with a doc string. So when you do a new module, or when you do especially a method, a class or a method, there should be a doc string, which is this triple quote. And you need to have information in there about what the code is. All of that information is then extracted by Sphinx, and it generates our documentation automatically. So you need to make sure that what is written in there is accurate and that it is informative. So a few examples, you'll see a lot where we do parameters. The parameters that are the inputs to your function, you do it like this. It's the variable name, colon, type, description of it. We always try and put the type if we can. You'll also do a returns over your things. If there's no name for it, you just put the type and then a description of what it's returning. All of this, again, will be generated into HTML documentation on the OpenPathSampling site, which I'll just show you what some of that looks like. So let's just pick one somewhat at random. So all of this is automatically generated stuff. If I look at the all-in X ensemble, you have here a few that give some descriptions. Some things we are better on our own at describing things than others. Here's a good long description of what something does, what the parameters it takes are, what it will return, and I guess that one doesn't do what it returns. But yeah, all of these details are generated automatically from the source code by using this. So that's just the practical stuff. Now let's talk about sort of the specifics of the parts that you will be developing. We'll start out with engines at the top of the page. So again, really important to those of you who are going to be working on CP2K, of which no one is here right now, but good thing this is recorded. We have two APIs for our engines. We have what we call the Direct API, which is if your underlying engine has a Python API already, we just wrap around that. That's what we do with OpenMM. Then we have the Indirect API. If you don't have a Python API, we'll go by way of the file system. This is what we do with Gromacs. The APIs are pretty simple. The Direct API, you need to be able to get the next frame. You need to be able to set and extract the current snapshot. And we do that as an @property. We talked a little bit about that earlier, the property decorator. And sometimes, depending on the engine, you might need to do something before you start the trajectory and something after you end the trajectory. So there's a start and a stop method. With this, if you can implement this for an engine, then that's all you need and the engine works. It does everything it needs to do in OPS. The Indirect API, going through the file system, is a little bit more complicated, but not really too bad. First off, you need to be able to read and write files in the format that the engine uses, because we're using the file system. then sometimes you need to do something before you start running the trajectory. That's the prepare step. So for example, with Gromacs, for those of you who know Gromacs, you have to gromp you'll have written out the file as a frame using maybe as a .gro, I think is what we do. Then you have to gromp that to make the file that's actually runnable. And so that's what the prepare stage does. Then the engine command is literally just something that returns a string that is the command that you run at the command line to run this engine, to run this stage. It can be made up of file names. Obviously, you're going to be writing files, so you'll have some file that has a number associated with it. And that's what the next thing is about. The set file names will internally store what the files are called based on the number that we're using. And the number just increments every time the engine is attempted, or every time the trajectory is made with the engine. And then at the end of it all, we do a cleanup. And so that, for example, if you have temporary files that you want to delete, that's where you would do that. So this is the Indirect API. Again, if you're familiar with the engine that you're working with, this is pretty straightforward to implement. So also in the context of engines, we talked about snapshot features. Snapshot features are the fields that tell about a snapshot, like coordinates, velocities, and box vectors. And if you want to make a custom one of those, for example, with something like CP2K, you might want to have the wave function information stored. That's what these objects do. So your engine overall will have the structure where it's in, actually you won't put it in OpenPathSampling/engines, you'll have it in your own repository, but it'll have my engine, then it has the init.py, because every package in Python has that in it. It has some engine.py that has all the information in it that you need to describe your engine. Then it has a features subpackage that'll have an init.py and then any additional features that you need to create. What do those features look like? What is the code for those features? Well, the main thing is that they need to tell, or sorry, first, how do we use those features? It's very easy. Once you've defined it like that, you import these features, and then all you do is you attach it using this attach features decorator. So there's a decorator that Jan Hendrik wrote that we are still using. And then you don't have to do anything else. What's really cool about this is that the code writes itself. Actually, John talked about the proper word. It's metaprogramming. The code is writing itself here. So all of the details about how do you copy this stuff, how do you store it, all of that needs to be associated with the snapshot object. But you don't have to write that for the snapshot. This decorator writes it for you. The details of the object are automatically implemented by OPS. And this is actually, in my opinion, this is one of the coolest bits of code in our package. And Jan Hendrik gets all the credit for it. He's the one who wrote it. So another way of saying that the code writes itself, yo dog, I heard you like programming. So JHP wrote code that writes code, so you can program while you program. It's the good life, I've got to say. So now actually doing these snapshot features, here's an example of one of our features. This is how we do coordinates within the toy engine. In this case, we're going to save all the details with each snapshot. So first off, you do see there's a docstring explaining it. This is NumPy doc format, docstring. Then you have to know what the variables are, and we say it's also a NumPy in this case. It's going to be stored in NumPy. It needs to know the dimensions that are associated with it because it's going to be stored. And then this is all netcdf+. I'll talk more about storage later on in this, but you just have to tell that netcdf+ that we're going to create a variable that's called coordinates. Its type is NumPy float2 because the storage needs to know types. Tells about the dimensions, you got to tell what it is, and the chunk sizes tell you something about how it will be reloaded. This is something you need for efficiency in loading. And this is what you need in the features.coordinate/coordinates.py. Obviously, you'd have something else for velocities, something else for box vectors. This is just one of these. But all it is what is it? How do you store it? That's what you need to tell. This gets a little bit more complicated in other cases. So the things we use with OpenMM, for example, we have separated out what we call statics and kinetics. And part of the reason for that is the snapshot object itself does what's called lazy loading. And again, that'll come up again in storage. But the idea is that we don't actually need to have all of the coordinate information every time we want to know about a snapshot. A trajectory is a list of snapshots. If I want to know the length of a trajectory, I don't need all of the coordinates that were used in that trajectory. That's very slow if you try to load them all. So what we do here, we have created this static container and kinetic container. In this case, we have to be able to do the same thing as we did before, where we're going to store an object that is a statics object, and it's a lazy object as well, and it's called statics. So that information is still all in here. Again, this is just about the storage. Now, the question then becomes, how do we get the coordinates out of that? And the answer is that we create a property. It's, again, an at property here. And that will programmatically extract the coordinates from the static. So you still say snapshot.coordinates, but it will get the coordinates. But until you say snapshot.coordinates, it never looks for the coordinates. So what we do here, if it hasn't already been loaded, it will load the, if it has, as long as the statics is there, it'll load the coordinates. Otherwise, there's a problem. And there's also a way to set it. This is how you set things using a property. So yet another way to do this, which again we'll use a property to get things, is the external snapshot, which is what we used with Gromacs. In this case, the OPS storage, the netcdf file that OPS uses, never actually stores the coordinates at any time. Those are in external files. And so you need to know from that, you need the file name and the frame number. And so the snapshot itself, all it ever stores is the file name and the frame number within that file that this snapshot is associated with. To get the coordinates now, you have, again, a property called coordinates. And somewhere the snapshot has associated with it. So instead of just having a pass on it and attaching the features and not having anything else, they attach the features, and then I have a method called load coordinates that will pull in your coordinates. This is not actually how we do it. This is simplified a little bit. What we actually do, because if you're going to load coordinates out of Gromacs, it's just as easy to simultaneously load coordinates, velocities, and box vectors. So if we load coordinates, we load all three, and we store all of that information at once. But this is the principle of how it works. So yeah, that was it on engines. Are there any questions about that? Yeah, Peter.
Well, first of all, in this slide here, you say the APS never stores coordinates, but here you store the coordinates. So
No. No, OPS does not store the coordinates on disk. The netcdf file does not ever have the coordinates. OPS reads the coordinates from the XTC file. Yes. Yes.
The other thing was that when you're talking about creating looking for the next snapshots, then you assume that your trajectory generator or engine is actually working frame by frame. Is that correct? So it does one frame and then it stops. Or something like that. So how could I have in mind if you run Gromacs, it just does X frames.
So what you mean? You're thinking about? Let me go back to that slide. You are thinking in the context of like this slide, right? So yes. Well, this doesn't work. This isn't how we do it with Gromacs. Now, in principle, actually, there is something that does that. But what happens here? So this is if you have a Python API, which means that you can just say, "Give me the next frame." OpenMM, run the number of steps until we get the next frame. Tell me what that frame is. That's what happens here.
So it runs for X or N frames?
Yes.
N timestamp?
And it stops. That's what OpenMM does.
Yeah, okay.
With Gromacs, we're using this. And what's happening is it is reading it. So internally, it still is using getNextFrame. But getNextFrame works by reading frame from file, looking for the next frame in that file. If there is no such frame, it pauses, it waits. It has a trick that it automatically optimizes the wait time so that you don't pull constantly. And then it runs again after some time and checks again to see if there's a new frame in that trajectory file, in that XTC file.
So then you assume that in parallel somewhere runs an independent Gromacs engine.
Yes, yes, it's a sub-process approach.
To stop and to start. I don't see that right here. Is that the engine command or something?
There is, so here we use inter-process communication. So engine command will start it. So the start process, again, actually, Indirect API implements the direct API. So there is a start and there is a stop. This is what's actually called by the code internally, start and stop. But then that will call things within the indirect API, like it uses engine command and starts a subprocess to start the thing, but it also has to prepare before that. So it's prepare, then figure out what that is and run it. Then the stop process, you can change what it uses, but we use a kill signal. We use actually a sig term to stop it. With Gromacs, it receives a sig term, it cleans up and stops. And so that happens all automatically. Now you can optionally customize what that signal is if you'd rather use a kill sig, sig kill instead of sig term. And then the cleanup also is part of the stop. Yeah. Yep. So collective variables is the next part. So that's where you'll be working on wrapping around plumed in particular. So talk a little bit about collective variables as things that you already saw yesterday, pretty much. So yeah, it's that part of the process. Simplest collective variable, you define a function yourself in Python, call it position x, and it returns, so this is atom 0, position 0 within the xyz. That's the first one is the atom number, then it's the position within xyz. So 0, 0 is x, 0, 1 would be y. So you make a collective variable by just wrapping around that function, the coordinate function around that function. Pretty easy. In principle, though, you often might have one function that's useful for in multiple cases. For example, you can calculate distance, but there may be more than one time that you will, more than one distance that you'll calculate using the same distance function. Here's one where we have different centers in a space, and we have a distance from that, so it's a circle in 2D around that. And we have, because we have different centers, we have different CVs. The way you do that, again, you have a snapshot, you have some additional parameter, additional keyword, and here you must give the keyword as a keyword argument. It must be center equals. You can't just give the array there. It won't know what to do then. But so this is all great, and with this we could write a function for a dihedral, and we could do this. We could write a function for distances using over periodic boundaries. We could do that. But why would we write functions like that when other people have done it before? Why reinvent the wheel? MD Traj has very kindly already developed all of these things for me, and so for example, we'll use MD Traj and wrap around something where we have the name. md.compute dihedrals, so we're using MD Traj's compute dihedrals function. We pass in a topology. That's an efficiency thing, actually, so you can add a few extra things that may be required because plumed might want something for efficiency. In fact, for plumed, you might, instead of giving it the function, you may actually be giving it a file name. That's probably most likely. And then any other things that you might need, like indices, anything else that needs to be passed to the function that you've written will be passed as keyword arguments. So one of the things that these do, these use simplified classes where we have a whole lot of arguments in principle to these methods, but we simplify them in order to well, we have a very generic CV class that has a mess of arguments, which I guess I'll show in not this slide, but the next one. So I'll talk about that in just a moment. A few things you need to know about CVs and storage. First off, the function itself for each CV is stored. So the source code is serialized. John talked about serialization in the context of OpenMM, but we can also serialize functions and all classes in Python. And so the function itself is serialized, which means that you can load that CV again later and use it on new data, and it still works. And again, because of that, all functions that you use inside the CV must be in the namespace. So you might have noticed on that circle 2D thing, I had import math inside the definition of the function. That's normally not done in Python, but we have to do that in order to make sure you know what math.square root is in that case. And you can also, the other way to do this is to pass other CVs as arguments. So for example, that's often the case if you have, I expect this will be the case with plumed, you'll have something where you calculate using one plumed file a whole lot of different CVs. And so then what you'll do is you'll have the CV that calculates 10 different CVs at once will be used as an input to another CV that will extract each individual thing that you care about. It's just a list of 10 things, so that's really simple functions to write, but that makes it very easy to work with. The other thing is that the results for each CV can be stored. This is to avoid the expense of recalculating the CV or of loading very large coordinate files. But to do that, right now, it's off by default, so you must enable CV.enable disk cache. You must do that before running your CV. You can turn it off with CV.disable disk cache if you for some reason don't like that. There are a few cases with small systems where you might not do it. For example, if your system has if a snapshot is just an X and a Y coordinate, and you want to save the X coordinate and the Y coordinate as CVs, yeah, maybe you just don't disk cache that. That's a waste of space. Let's see, I think that's all I want to say about CV storage. Oh, that was the thing I was going to talk about. Yes. Yes, thank you. That is exactly the thing I thought there was something else I want to talk about. So, dangerous is how it is. However, we have, in a pull request, I think it's implemented, I just need to review it now. I think I literally put it in today. We have a pull request that it will have a new thing that allows you to enable a safe mode for loading CVs from storage. Once you've defined a storage object, there'll be a safe mode, and that will prevent that. That's actually a problem in another case, not just a security problem, but there's a difference, or at least if I'm understanding the error I've seen, there is a difference in the way that the serialization of functions happens in Python 2 and Python 3. There are some differences in byte treatments as well. That was another issue, but there seemed to be some issues with the actual serialization that we were having. So as a result, that way you can load, right now if you created a file with Python 2, you cannot load it for analysis with Python 3. So by turning on the safe mode, you will be able to do that. And then you can later attach the function, assuming you know what it is. And obviously important that the function does the same thing as it did before, otherwise any new things that you generate will be nonsense. But yeah. Yes, I'm glad you asked. That was exactly what. Yeah.
On the safety, currently it's in a way that it scans the code for which packages are important, and there's a list of safe imports, so you can use empty trash.
I thought we had disabled part of that though, because that was a problem.
Disabled, but this was I think there's some problems with people want to use additional packages.
Yeah. But there was a whitelist of packages that were supported, but I thought we had at least partly disabled that because, Sandra, do you remember? Because you were the one who needed that disabled.
This was the original concept, so that like now how you can use math, you can use the things, but not everything.
Yeah, that was the idea. So there was concerns about security from the beginning, but in principle, even that, I mean, somebody could do something that would be malicious enough and problematic. So yeah. Mm-hmm.
Usually you put it outside, but the way that in Python the function is stored, it just says take whatever map is at this point and run a function with it. So if you store the function without telling it, and the import map is not in the function, just storing it, it has no idea what map means. You can run the function, but unless you would write import map before running the function, it would just say, okay, map is not defined, I can't run this function.
Yeah. So if you create the name in the namespace before you try and run the function, that would still work. So if you didn't have import math in the function, and then but you did put it when you tried to run it later, that would still be okay. But yeah.
So the safe side is if you put everything that is required.
You should always put it in the function. Yes. Yep. That's what's meant by this. Yeah. Exactly. So I said that the CV classes are simplified. That's because there are a bunch of parameters associated with them. And here are the important ones, at least. So this has to do with how the CVs behave. And we usually have subclasses that set these in some default way that makes sense. So for example, because of the way OpenPathSampling works, every time you make a snapshot, because we're concerned about having path reversal moves, it's something that happens in TIS at least, it's very important. Every time you make a single snapshot, you actually make two. Now, they just copy the data. One of them knows that it's the forward, and one of them knows that it's the reverse. There's only one copy of the coordinates, only one copy of the velocities, but there are two snapshot objects with pointers to those coordinates and those velocities. One of them knows that it is the reversed version of it. If your CV is the same on both of those, you can make it faster to calculate by setting CV time reversible to true. Now that's going to be true certainly if it only depends on coordinates. It can be even true of velocity if it only depends on the magnitude of velocity, like velocity squared. So kinetic energy still is time reversible. In one snapshot, it doesn't matter whether it's forward or backward, but it does, even though it depends on the velocities. There's another one, CV requires lists. So a bunch of these, by the way, came out of working with MD Traj. And CV requires lists is true if the input and output of the function is a list, as it is with MD Traj. By taking lists, MD Traj is able to do its analysis much more efficiently, much faster than it would be if it did each frame individually. But what this means is that we have to take our snapshots, wrap them into a trajectory before sending it on to the CV, and then when we get something back from the CV, we have to unwrap it from being in a list, in a trajectory. Then the wrap NumPy array is kind of the other side of that. So if there's a complex function that doesn't support list processing, you can convert the final output to a NumPy array. I think Hendrik might be able to explain more on that than I do, because I never fully understood that one as well.
You can run CVs with single snapshots. You can say, like, give me the coordinates. You can also run it with a complete trajectory. It works exactly the same. So what it internally does is, I mean, the simplest thing would be just pick every snapshot single, call the CV function, and create a list of all the results. What you usually want is you want a complete NumPy array and not a list of NumPy arrays, right? This just, at the very end, just calls the
Makes it in the
NumPy.array around it.
Yeah. So then this last one is CV scalarized NumPy singletons. This is something that comes out of our experience with MD Traj. MD Traj, for example, if you want to compute distances, you notice that there's like two sets of brackets around those lists. If I go back to, there we go. If I go back here, you'll see there's two sets of brackets. That's because MD Traj will calculate this is only one distance, but MD Traj would simultaneously calculate 10 distances if I wanted it to. Which, again, it does this because it's a lot faster to calculate a lot of things at once than to load the snapshot into memory over and over again. So what that means is that the output of that is actually going to be a list of lists where the inner list each has one element in it, like this. Typically, that's not what we want. We actually want to turn that back into a normal list. And so that's what the scalarized NumPy singletons does. And again, therefore, because of all of these things, different subclasses of collective variable will have different defaults. And if you're making a new subclass, it's up to you to decide what makes most sense based on what's capable in, say, Bloomed. So now a little bit on CVs versus volumes versus ensembles, because this is a point of frequent confusion, because especially if you're not used to path sampling. In fact, even if you are, I think I've been guilty of making some of these confusions and certainly speaking incorrectly on some of these. So a collective variable is a snapshot maps to a real number. It's a function that converts a snapshot to a real number. Technically, in OPS, it can do more than just a real number, but simplify it, let's think of it as mapping to a real number. It's like the question, what is this dihedral angle? What is this distance? A volume, it's a region in phase space. It maps a snapshot to true or false. And so the question there is this dihedral within the range that defines my state? Is this distance within the range that defines my state? Is this distance inside or outside of my interface definition? An ensemble takes a trajectory and maps that to true or false. So does this trajectory involve a change from one state to another, if it's a TPS trajectory, for example? A TPS ensemble, that is. So just to sort of say this again with pictures, especially the last two, a volume, it's either in the volume or it's out of the volume. Any frame is either in the volume or out of the volume. An ensemble is about a trajectory. A trajectory is either in the ensemble or out of it. That's the case for path ensembles. So on to the next stage, which is these networks, transitions, and ensembles. I'm actually going to go kind of backwards here and tell you a little bit about the internals of how ensembles work, and then build up to why we have these network and transition objects. So one of the big ideas of OpenPath sampling is that we can break down complex path ensembles into very simple ones. This is a really new approach that it makes it so we can combine and create new path ensembles that have not been considered before, new ways of doing sampling that maybe would be completely new. That's the whole goal. So here I have an example of one of our sort of atomic ensembles. It's the all-in X ensemble. So what it means is that all frames in this trajectory are in volume called A. The X is a replacement for volume in this case, and so it's all of them are in A. So the question I have is, if you keep extending this trajectory, when will it not satisfy this ensemble? Can somebody tell me? If all frames have to be in the ensemble, when does this no longer satisfy the ensemble? When one frame is out. If it doesn't satisfy the ensemble, can you continue the trajectory until a time when it will again satisfy the ensemble? Nope. Once you have one frame out, you can never have all frames in. So these are the ideas. These are the questions that you need to ask as you're doing path sampling, is when do I know I can never be in this ensemble again? And so we have a few methods that are associated with the ensemble object. The first is just the call method on it, which just asks, does it satisfy the ensemble? But there are these other methods that are really important, like can append. Can append says, if I keep going, is there any chance I will still be in this ensemble? So if all of my frames so far are in the all-in X ensemble, yes, I can keep going. The first time I don't have a frame in that ensemble, no, I cannot keep going. And then there's an equivalent thing for going backwards in time called can prepend. We also have a split function, which will take any long trajectory and pull out the longest subtrajectories that satisfy that ensemble. The point is that this is all a bit of complex stuff, but you get it all for free. So here's another thing we use are sequential ensembles. So here is a TIS ensemble. You have an initial volume, a final volume, and the rules for the TIS ensemble are that you have to start with one frame in the initial volume. You have to have at least one frame that is outside of the interface, the red dashed line, and then the trajectory can end with one frame either in the initial volume or in the final volume. So how do we create these ensembles in OpenPath sampling? Well, we have an object called a sequential ensemble, and it just says you have to start out with one frame that is in A, then you have a bunch of frames that are not in either A or B, and at least one of them is outside of the interface, and then you have one frame that is in either A or B. And just by doing this, you automatically get that can append, can prepend, and split function with no additional effort. This is what's really exciting about OPS. These are sort of a very new idea, I would say, in terms of how this stuff is implemented, and very different from what's been done before. So if you're doing a real path sampling simulation, let's say that you have 3 ensembles from A to B, 3 ensembles from B to A, and so you end up with 6 total ensembles, and you can create each one of them like that. That's a bit tedious, and in larger, more realistic systems, you might have 8 states with 6 interfaces each. Furthermore, when you analyze this stuff, these things have to be grouped together. The ensemble that's telling you about going from B to A, begins in B, ends in A, with the outermost interface from that, that tells you nothing about the rate from A to B. That's not useful for calculating the rate from A to B. Just the ones that come out of A are useful for calculating the A to B rate. That one's used for the B to A rate instead. So we have to organize these into groups in order to do the analysis. And so we have each group like that is what we call a transition. All of the transitions in a network, or all the transitions joined together to make a transition network object. This is because we have many, many many transitions possible. Again, if you have multiple states, you may have, if you have 8 states, you have, what is it, 8 times 7 minus, or yeah, 8 times 7 divided by 2, right? Different transitions possible. So that's a lot. When you're calculating these things, now this gets into the idea of multiple state TIS. So here's our full rate matrix. So we don't worry about the A to A or B to B transitions, but there's not really a rate associated with that. We have all of these different transitions, which are the total number of transitions. So here we have 6 of them. When we calculate this stuff, again, this is TIS. We talked about the TIS a little bit yesterday. It's the flux times the probability of getting to the outermost interface times the probability of ending in state B, given that you got to the outermost interface. If you look at just one of these states, leaving A, you have the same thing for everything except for this last part. So you don't want to have to recalculate all parts of this for every one of those transitions that you might be interested in, not all 6 of those, or all, many more if you have a larger system. The only thing that's different is this one part that we call the conditional transition probability. So in MSTIS, we only actually run the TIS sampling over the A to anything transition. It starts in A, can end in any final state. The analysis transitions are the specific A to B, A to C transitions. The sampling transitions are the A to anything transitions. Again, this is multiple state approaches, in particular, multiple state TIS. So again, the sampling transitions are things that we are using in the sampling, and the goal there is to minimize the amount of work that we need to do. The analysis transitions, or just transitions is the name of the object in there, it contains all of the individual reactions that you care about, which could be quite a number. And when you make a transition network, it builds both of these so that it already knows from the simple information you give it in building the network, it knows all of this stuff, and you have all that information immediately available. On to path movers and move schemes and move strategies. So this is also one of the more complicated things. Again, I think if I remember correctly, this goes from the path mover to the move scheme to try and give you a reason that we have these more complicated objects. So the big ideas are that the path mover takes a sample set as an input and returns a move change. Now that's a little bit strange, but remember that we store all this information about how the move changed and what happened during the move. So the sample set, the what you sampled isn't the only thing that matters. We care about how you sampled as well, and from how you sampled, we can extract what you sampled. And when you do this, Metropolis Monte Carlo is already built in. All you have to do is return a trial sample and I believe any details about the process using the call method. So here's an example. You create a path mover. It takes an ensemble as input, the ensemble that it works on. This is an important thing. Each path mover is assigned to a specific ensemble. So a shooting mover is for a specific ensemble that it's shooting in. A replica exchange is for a specific pair of ensembles that you do a replica exchange between. And then you can have any other options that might come with it that detail how the move works. So this is the initialization. You need to define a couple of things that are the called ensembles, which are the things that go as the input to call, which you'll see in a moment, and the input ensembles as well, which is usually going to be the same. You might also need the output ensembles, which is usually the same as the input ensembles as well. So when you call, the input to the call function is a sample. Remember, the sample it already contains inside of it a trajectory and the ensemble that trajectory is associated with, which should be the ensemble that you're using this mover on. You can have more than one sample as well, like replica exchange, of course, has more than one sample. Anything that you do to make the trial sample, you should store any details that are of any interest in an object called details. Then you return a list of trial samples, even if there's only one, return a list, and this dictionary of details that might be of interest for analysis later. So again, just like how we had a lot of ensembles, because we have an ensemble for every mover, we end up with a lot of path movers. This is the same thing we showed you yesterday, that you have all of these different movers associated with every ensemble. It ends up being a really big and complicated thing. Furthermore, we want to make it really easy for you to change aspects of this move scheme, whether you want to change the options for the mover. Maybe you want to switch to two-way shooting instead of one-way shooting. Maybe you want to switch the shooting point selector that you use. Maybe you want to change which ensembles are involved in your replica exchange scheme. All of that, we want to make that really easy, and we want to make that such that the user can do it without having to worry about the order that things are built in. Because this is the hard part. If you're building a big structure like this, the order that you build this tree in is very important. And if you try to change the tree after it's already built, after an important part of it's already built, it can be very hard to get the structure that you expect. So because of that, we use these move strategy objects and move schemes. So the move scheme has inside of it a list of move strategies, and then when the move scheme needs to, it will apply those strategies to create the move decision tree. The move decision tree is this thing. So the move strategy actually gives the details of how to build the mover. There's a strategy for how you build a one-way shooting mover. And that says, here's a list of one-way shooting movers. There's a strategy for doing nearest neighbor replica exchange. There's another strategy for doing all replica exchanges within the same interface set. There's another strategy that says, in addition to the replica exchanges I already have, I want to add this specific pair of replicas to be exchanged. So these are the sorts of things that the strategies do. The strategies, the internal code on this is quite complicated, but what you have to do as someone developing one of these things is much easier. All you have to do is assign a level to it, and I'll talk a little bit about the level in a moment, but that's what gives you this sorting by what order the tree needs to be built in. And then you need to say any options you want for it. If you want to customize any ensembles, the group that it's associated with, that's like shooting, replica exchange. For example, if you're adding stone skipping, you might decide that stone skipping is a replacement for a shooting move. And so you might want the group to be called shooting. But a user can then initialize this with a different group name. So the default could be shooting, but maybe I want to do shooting and stone skipping. In that case, all I would have to do is add the stone skipping strategy with a group called stone skipping instead of shooting, and I would have the default shooting and stone skipping as well. And everything else just happens automatically. And so you set it up like this. You have to have something that makes the movers. This is a trick that will get the ensembles that you need. You probably won't need to override that. In rare cases, you might need to override the get init ensembles. And then from this ensemble list, that's the list of ensembles, you just apply to figure out what, to make the movers that you need. You just apply those to make one mover per ensemble. Yeah, Sander. That's actually a bit complicated, and it depends on what the level is. But usually it means that we're overriding things at that level. So if you have a mover level scheme, replacing the movers would remove everything from that group as well and replace it. So this is a case where technically the thing that says in replica exchange, it's the best, easiest example, that I want to, the strategy that says I want to add another replica exchange to my list. That by default does not replace anything. If you said that it would replace something, it would remove all replica exchanges and you'd have only that one. So that's the flexibility that enables. Anything else? So here's about this sorting, this ordering for move scheme and move strategy. So we have several different group levels defined. We call them signature, mover, group, supergroup, global. Honestly, these two are not very well defined what they are. The global mover decides, for example, do you look by replica, or do you look by ensemble first, or do you look by the move type first? So we've always shown you things where the first decision you make is what kind of move am I going to do? But for example, that doesn't work. You can't sort your groups based on the move type if you're doing a single replica TIS, where the single replica has to know which replica it is first, because different move types might be available for different replicas. So that handles that part. don't worry too much about what each of these levels means. I would say if you're implementing this, you can just look at something that's very similar. I mean, stone skipping is going to be basically the same as a shooting move, and as will the, it's called S selection. What's the? Shooting range. Shooting range, yeah. So the shooting range will also basically be a shooting mover. So looking at the shooting mover will tell you everything you need to know to do that. But the trick is, and again, this has to do with the fact that building this tree has to be done in the right order, otherwise it all falls apart. But the user might not put things in the right order. That's why we do this. So let's say I start out with something. The first thing I give it is something that's a signature level mover. Great, it builds up as a signature level mover. That's the first thing that I'll do.
So that is, for example, a replica.
Yes, it could be a replica exchange. Don't worry about specific movers, just the ideas here of the ordering is what matters. Now the next one I give to is a mover level strategy. And so that is going to be the first of the mover level strategies to be applied. But then the third thing I gave was another signature level strategy. And so that will get applied actually before the second thing, before the mover is applied. So it will build 1, 3, and then 2. As I go on, now I did something that's global level. I said I want this thing to be my, I want this to be a choose the type of move first type strategy. And now I've added some more. So even though the order in which they were added by the user is 1, 2, 3, 4, 5, 6, the order in which the tree is built, which is what needs to actually work, will be 1, 3, 2, 5, 6, 4. The problem is, especially you put the global part first, you've already at this point defined what all of the move types that are allowed are. And maybe that changes when you add new movers. So, the global is a decision of, do you select by the move type, which is what we normally do. The first choice is what type of move are you going to do? Or do you select by the ensemble first? That's the examples we have implemented. If you're doing single replica TIS, you need to look at what your ensemble is before you can choose a move. Because if you try to do a minus move in an ensemble that doesn't have the minus move supported, you're going to have some problems. So any other questions about that? That part is actually one of the more complicated aspects, especially this reordering thing is quite confusing. So those of you who are implementing these things may have questions later. For what it's worth, conceptually it's confusing. In practice, what you have to do is actually really easy because it's just like everything else that is similar to it, and it doesn't take a whole lot of code to write.
Is there a way to test your build?
Yes, you can visualize the move decision tree. And we should have shown that at some point. We don't. We have examples that do that. These pictures I've shown that look like, go back to it. The picture I've shown like this. This is generated by code. This picture is not like some picture that I made in Photoshop. This is generated by code. You can generate this for any tree that you've done, and that would be the way to check it. In fact, that's probably, we only give you examples where you're using very simple default schemes in these tutorials. But if you ever change your move scheme or if you add move strategies, you should always take a look and make sure you got exactly what you were expecting using this. There are examples, if you look at the move strategies and move schemes examples in the OPS documentation, there are examples that do that show you how to use that. So storage is almost the last thing. We skipped over the initial conditions again because a sample set we already talked about yesterday. I like to say that the thing about storage as we have a couple of terms here. We're going to talk about storage and stores. And I like to think about storage as the whole bookshelf. It's everything that's in there. It is your file. A store is an individual shelf, and you'll have different sized shelves that will hold different objects. So some examples of these shelves are we have storage.steps, which is the right size to hold a step. Storage.trajectories, it's the right size to hold a trajectory. Storage.snapshots, it's the right size to hold a snapshot. We also have a very special shelf that will hold any kind of object, storage.tag, and so you can do storage.tag, and then you use it like a dictionary. And anything that is storable by OPS, which includes all the Python basic types. So if you have, I've used this in the past where I had results that had come out in terms of a dictionary that I'd created, and I wanted to store that information to share it with colleagues who I was collaborating with. And so I just put it in storage.tag, and it works great. So there are different levels of code that we're working with here. And so first off, all of our storage, at least at this point, is built off of netcdf4, which is a general package used broadly within the scientific community for data storage. On top of that, Jan Hendrik has written what we call netcdf plus, which will eventually be separated outside of OPS because it's useful beyond just OPS. But right now, it's Python extensions to netcdf that were developed as a part of OPS, so it's inside the OPS code. Then you get to the details of what OPS needs to talk about. What's a trajectory, what's a snapshot, things like that. Those are in OpenPathSampling.storage. And so that's defining the shelves that we need to work with. When you're working with OPS, all objects that are storable in OPS are either Python built-ins or inherit from either netcdf plus storable object or netcdf plus storable named object. The objects that you'll be creating will probably all be inheriting from storable named object. That might not be immediately obvious because if you'll be implementing something that directly inherits from a path mover. But if you keep going up that tree, you'll see that path mover, actually it might be something that inherits from engine mover, which inherits from path mover, which inherits from storable named object. So that's, all of this the point is, though, by inheriting from this stuff, you'll automatically get the features that I'm about to talk about. So, important ideas about storage. First off, objects in OpenPathSampling are immutable. Once the object has been saved, you must not change it. Any change that you do make to it will not be updated in the file. So you never want data to change. There are some cases where you might change something about functioning. So for example, a path simulator will be stored, but maybe you want to change how often it synchronizes to disk. There's a choice to do that, a save frequency, which for toy models, you want the save frequency to be relatively infrequent, once every 100 steps. But for an expensive calculation, you want to save after every step. So that's something that it's OK to change that because it doesn't change. It changes sort of the behavior in timing. It changes your experience of the code, but it does not change the output in any way. On the other hand, you have a volume that has a fixed minimum value of the order parameter, a fixed maximum value. Do not change that once you've done it. That will break anything that you've already saved. Additionally, objects in OpenPathSampling use universal unique identifiers. And this is a great trick that lets you use these things across different files. So you can actually split your OpenPathSampling stuff across several files. You can pull out only part of your calculation. Like if you had a huge calculation, in fact, I'll say the thing you ran yesterday, the analysis you did yesterday was 250 megabytes. Seems like a lot. That was only the collective variables. I had split off only the collective variable stuff, the stored collective variable results, from a file that when it had all of the data in it, it was, I think, 20 gigabytes, something like that. So, but it still would have, the important thing is that if I'd done an analysis with that, the ensemble objects, which were saved in both, would still recognize each other because they have the same unique universal identifier. So across files, across machines, these give you a way to do this. It's also really useful for some more advanced database stuff, like we're looking at moving towards things like MongoDB, where these unique universal identifiers are really important if you're going to do a very large distributed database type of approach. Also, things in OPS, at least the data objects, are lazy loading as much as possible. So this is what we talked about before, that if you're loading a snapshot, if you don't need the coordinates, don't load the coordinates. It's just a waste of time and can be really expensive if you do otherwise. So how do we actually store things? If you're going to store an object in Python, you need to serialize it. John talked about that with OpenMM, that it can serialize. There are lots of different ways to serialize. XML, as John said, is a really large way to serialize. Ours is still somewhat large, but not quite as bad. So we don't do quite the same thing for snapshot data, for things like the NumPy arrays, but this is what we do for simulation objects, like path movers. You take the object, and there's a method associated with that object called toDict, and that turns it into a Python dictionary. Those of you who know a lot of the details of Python know that Python objects are pretty much internally dictionaries anyway, so this is pretty easy to do. And then we take that dictionary, and there's some internal stuff within netcdf plus that will turn it into a JSON string, and that JSON string is what gets actually stored. For most simple cases, the default versions of toDict and fromDict will work just fine. So if you have a case like this, I've created an object that has 2 parameters. I store those parameters with the same names, that's important, in the object. And then I have something where I say, well, I don't actually need to save this object, so I can create it using whatever function. It doesn't need to be saved. It's a new object, though. Those things, that will store and restore just fine. You don't need to do anything at all for it to work with storage. Where you can get into weird things is if you are creating something fancy in there that you actually need to store. So for example, during the initialization of a network, it creates the transitions and it creates the ensembles that are associated with the process. So those ensembles need to be stored, and it's really important that you don't overwrite the ensembles that you had before when you restore that network. You want the same ensembles associated with it. In cases like that, you'll have to do something custom in the dictionary, in the toDict and fromDict methods. So yeah, toDict is going to the dictionary. There's an analogous fromDict that brings it from a dictionary. Be careful about cyclic definitions. Jan Hendrik says it should work, but I believe we have a problem in at least one of our packages that Sander has worked on where if 2 things refer to each other, you can end up with difficulties in storage. So there are edge cases where that doesn't work. There are some cases where it does. When I say infinite loop, this is not like the code is going to freeze in the process. What will happen instead is it'll give you a very long error message because it'll hit a recursion depth with Python. So any questions about storage? All right, then the path simulators. It's the last part here. So if I can get to it, there we go. So the path simulator is sort of, as Johnny said today, when you do object-oriented programming, there isn't a main function in the code, or not as such in these sorts of, in a Python library at least. But the path simulator is what kind of takes the place of your main function. So again, I think that PPTIS will actually work with the path simulator that we already have. But if you were to do forward flux sampling, you would have to create a new approach, a new path simulator. You have a lot of flexibility here because this is the outermost layer of the code, so there's not a whole lot that you have to be super careful about. But a few things just to make it work like everything else. It should take, the output file should be the input, or the parameter for the output file should be called storage, just like everything else, we call that storage. There's already a function called run that should run the simulation. Usually that takes something like number of steps as its argument. Any output that you write, instead of using a print function, you should always output it to self.outputStream. That will default to acting like a print function. It'll default to using sys.standardout. But the point is that if the user wants your output to be redirected to a file and wants to do that in code rather than trying to do that on the command line with the redirect, this gives the user a way of just saying, when they set up the simulation, that the output stream goes somewhere else. This, by the way, is another example of something where it changes the behavior, but it doesn't change what's saved, so it doesn't matter. Whereas most things should be immutable, changing the output stream, that's not a problem. And again, the save frequency is something that controls how frequently you save sync data to file storage. Most cases, you'll default that to 1, so that after every step you save, but you might want to do something different than that. So that is what I have for this, I believe. I think that's it. That's extra slides. So are there any other questions?